Hi guys, we're going to talk about covalent bonding today, and we're going to continue with covalent bonding for quite a while. Today we're going to focus on what is covalent bonding and how to draw Lewis dot structures for covalent substances. So we're going to start with the definition of covalent bonding, and it's when two or more nonmetals bond together. And remember that nonmetals want to gain electrons to become like noble gases. And so because they all want to gain electrons, they end up sharing. In fact, covalent, co means together, and valent means valence electrons. So the valence electrons are shared together. So they share their electrons. Again, this means together. And this is referring to the valence electrons. So when we say that they try to achieve a noble gas configuration, if you look at the noble gases, most of them have 8 valence electrons, right? Their S's and their P's are filled with 8 valence electrons. So most atoms, when they share electrons, they are trying to get to 8 electrons. We call that an octet because it's 8. Helium is an exception. It only has 2 valence electrons. So atoms that are close to helium, they become stable if they become like helium with 2 valence electrons. And mostly that is hydrogen. So hydrogen is good with a duet, 2 valence electrons. All the other atoms tend to try to get to an octet with 8 valence electrons. So when you draw Lewis dot structures for covalent substances, what you want to do is you want to write out your symbols. And you want to draw your valence electrons. So hydrogen only has 1 valence electron. Now remember we said you there's a certain order to write your valence electrons. That does not exist. It does not apply when we're doing covalent bonding. So instead of putting my electron here for the hydrogen, I'm going to put it right there. Now, it's not a problem if you put it in the wrong spot. You can always move it. So once you draw them, if they are being shared, you can move them around if you'd like. So you can erase it and move it somewhere else. So I'm going to draw my valence electron here. And then you connect each pair of atoms. We have only one pair here, so you connect those. And whatever is connected, whatever is shared, so this is a bond, that means that it's shared for both atoms. So those 2 electrons count for this hydrogen and also for this hydrogen. So this hydrogen has 2 electrons, it's good with its duet. This hydrogen has 2 electrons, it's good with its duet, so that's perfect. So now you just rewrite it so it looks a little bit neater, so it looks like this. Let's try HCl. So we have hydrogen and chlorine. Hydrogen has 1 valence electron, chlorine has 7. So 3, 4, 5, 6, 7. Notice that I left my single electron on this side because I know it's going to bond, but no problem if you put it in a different spot. You can always erase it and move it around. So connect your pair of atoms and then count. So now this hydrogen has 1, 2, so it's good with its duet. This chlorine has 1, 2, and then 3, 4, 5, 6, 7, 8. It has its octet, so everybody's stable. So just rewrite it so it looks a little neater. So it looks like this. Let's try H2O. Oxygen and 2 hydrogens. So hydrogen, each of them have 1. Oxygen has 1, 2, 3, 4, 5, 6. Connect each pair of atoms once and count. So we have this hydrogen has 1, 2. This hydrogen has 1, 2. So both hydrogens are good with their duets. The oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen's good. Again, just rewrite it so it looks a little neater. Oops, sorry. Let's do it right here. Okay, let's try maybe nitrogen. So N2. So we have 2 nitrogen atoms, each have 5 valence electrons. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Connect once, and let's count. So right now, this nitrogen has 1, 2, 3, 4, 5, 6. This nitrogen also has 1, 2, 3, 4, 5, 6. They both only have 6. They'd like to have 8. So if they both want more, then connect another pair. So let's connect this pair right here, and let's count. So now this nitrogen has 4 that are being shared, right? And then 4 that are being shared, and then 5, 6, 7. This nitrogen has the 4 that are being shared, and then 5, 6, 7. They both want more because they both have 7, and they want 8. So connect a third pair and count. So now 1, 2, 3, 4, 5, 6 being shared, 7, 8. This one's good. This one, 6 are being shared, and 7, 8. That's perfect. So now just rewrite it so it looks neater. So that looks like there's a triple bond between the two nitrogens here. So when you draw these on the test, they do have to look neat. They have to look like this. This would not be acceptable. So when you have multiple bonds, you put them all on top of each other like this. When you have extra electrons, we call those lone pairs. Pairs meaning they exist in twos. So this would not be okay putting them separate like this. They have to be in twos. See how like these are in twos, these are in twos. So those are called lone pairs. Another little tip is if you look down here, this might be helpful. It doesn't work 100% of the time, but it helps like, I'd say 90% of the time. Honk, I don't know if you remember this or if you were taught this in biology, but honk represents 1, 2, 3, 4 are the number of bonds that these atoms can make. So H stands for hydrogen or halogens. Hydrogen or halogens usually only make 1 bond. Oxygen usually makes 2 bonds, nitrogen 3 bonds, carbon 4 bonds. So sometimes that is helpful, like nitrogen makes 3 bonds. Look at this. Nitrogen's making 3 bonds. Oxygen making 2 bonds. Look at this one. 2. Hydrogens and halogens only make 1 bond. So most of the time that works. Not 100% of the time, but most of the time. So that's a good thing to kind of keep in the back of your mind. So that's a tip there. Let's skip number 2. Let's go to number 3. Another tip is that you want to draw lone pairs next to each other, like in water. So let's go back to water. And we drew it this way. Another way to draw water, which is perfectly acceptable, is like this. And again, this is perfectly acceptable. Either one of those would get you all the points for drawing the Lewis dot structures. However, when we start learning about bond angles and shapes of molecules and stuff like that, you are likely to get those correct if you draw the lone pairs adjacent to each other, next to each other like this, not opposite of each other like that. And so both of them would get you the points for the Lewis dot structure, but I highly recommend that you draw your lone pairs next to each other like this because you're likely to answer the other questions correctly. Let's do one more. Let's do number 11 together. C2H4, so it looks like we have 2 carbons and 4 hydrogens. Now, based on this honk, I kind of know that carbon takes 4 bonds and hydrogen only takes 1 bond, right? So that helps me realize, oh, if I have carbons and hydrogens, the carbons are probably in the middle and the hydrogens are on the outside because hydrogens and halogens can only form 1 bond, which means they have to be on the outside. So I'm going to put the carbons next to each other, and next to each of the carbons I'll put 2 hydrogens so that I have a total of 4 hydrogens and 2 carbons. I'm going to then put my valence electrons, so each hydrogen has 1. Carbon each has 4. 1, 2, 3, 4. Then you connect each pair of atoms once. So I'm going to connect this carbon to the hydrogen, this carbon to the hydrogen, this carbon to the hydrogen, here to the hydrogen, and then I'm also going to connect my 2 carbons. And then now let's count. So each of the hydrogens are okay right now. They all have a duet. This hydrogen has 1, 2, this hydrogen has 1, 2, this hydrogen has 1, 2, this hydrogen has 1, 2. Let's look at the carbons. So there are 2 being shared right here, 1, 2, 3, 4, 5, 6, 7. This carbon only has 7. Let's look at the other carbon. 1, 2 in the bond here, 3, 4, 5, 6, 7. They both only have 7, so they both want more. So let's connect to the other set. And now let's count. Now when you count, there are 4 between them, 5, 6, 7, 8. And for this carbon, 1, 2, 3, 4, 5, 6, 7, 8. So now they're all good. So now make sure that you draw it correctly, or a little bit neater. So you would want to draw it like this. So we went over these tips down here. We skipped over this little tip here. There is a math way to figure out how many bonds to draw. And it's kind of a lot of work, but sometimes when you're stuck, it is helpful. I don't think it's very helpful when they are simple molecules, but when it's pretty complicated, then it's pretty helpful. So I want to show you this with carbon monoxide. So for carbon monoxide, let's try to draw it. We have carbon, and carbon has 4 valence electrons. Oxygen has 6. 1, 2, 3, 4, 5, 6. And let's try to bond them once. Right now, this carbon has 5. This oxygen has 7. So they both want more, so let's bond another pair. Now the carbon has 6, so it needs more, but the oxygen already has 8. If we try to bond a third pair, what's the problem with that? Well, carbon has 7, but now oxygen has like 9. That's more than it wants, so this does not work. So when you get stuck like this, you can do the math. So let's do the math together. So for carbon monoxide, what you do is you calculate the number of valence electrons needed to make each atom or element stable. So 2 for elements before boron, like hydrogen, and 8 for everything else. So I have a carbon and I have an oxygen. So for letter A, my carbon needs 8, my oxygen needs 8. That's a total of 16 electrons needed. Okay, let's look at B. B says, calculate the number of valence electrons available for your atoms. So carbon has 4 valence electrons. Oxygen has 6 valence electrons, for a total of 10 electrons available. Letter C. Subtract A minus B, and this gives you the number of electrons shared. So if I subtract these, 16 minus 10 is 6 electrons that are being shared. And so that's my letter C. So I need a total of 16, but I only have 10 electrons, so that means 6 of these electrons need to be shared together. Letter D. Divide C by 2, and this gives you the number of bonds in the molecule. So I'm going to divide this number by 2, and this gives me 3 bonds, because each bond has 2 electrons, so if we're sharing 6 electrons, that means we have 3 bonds. Okay? Part E. Draw the bonds and add lone pairs so that each atom is stable with a duet or an octet. So what that means is I'm going to draw carbon and oxygen, and I'm going to draw 3 bonds. So 1, 2, 3. There's only one spot for the bonds here, so I'm going to draw the 3 bonds in between them. And then I'm going to draw this bond right here, so it just looks a little bit neater. Okay, and you also want to add lone pairs so that each atom is stable with a duet and octet. So carbon is stable and it has 8, so right now it has 6, so I'm going to do 1 lone pair here. Oxygen is stable with 8. Right now it has 6, so I'm going to put a lone pair here. Okay. Letter F, count the number of electrons drawn. This should equal to the electrons available in part B. This is very important. You want to check that you did it correctly. So we're going to count how many electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total. That should equal to the number in B, which is 10 electrons available. So that means we did it correctly. So this helps you with really hard molecules to draw. It's kind of a long process. It'll help you when it's really complicated like this, but if it's a simple molecule, I don't recommend that you do your math. Now, how is this possible? Well, there's something called coordinate covalent bonds. They exist sometimes. There's not really a way for you to figure out that it is a coordinate covalent other than me telling you or just your experience. So you need to know that carbon monoxide is one that forms coordinate covalent. So what does that mean? Coordinate covalent bond is a bond in which one atom contributes both bonding electrons. So I'm going to redraw this. 1, 2, 3, 4, 5, 6. And I'm going to draw these with a different color maybe. Let's do red. 1, 2, 3, 4. Okay, so we're going to bond the first pair right here. Good. Another pair right here. Good. Now carbon has 6, oxygen has 8. So oxygen's already good with its octet. Like we saw before, we don't want to make a third bond between, this electron and maybe this electron, because then oxygen would have too many. So what happens? Well, carbon's not okay, but oxygen is okay. So then oxygen says, don't worry, carbon, I'm going to help you out. I have already the electrons that I need. So what I'm going to do is I'm going to take 2 of my electrons. So I'm going to go ahead and erase those 2 electrons here. Okay, there's my oxygen. So instead of having the electrons with the oxygen decides it's going to put its electrons in between them to share. And it's going to form a third bond right here. But notice that that third bond, both electrons are coming from the oxygen, not one from each. This is called a coordinate covalent bond. And again, it just sometimes happens. You would not know unless you're just, you practice a lot. So the one that you need to know about is carbon monoxide. Otherwise, I will tell you if there is a coordinate covalent. And so that's how we get this molecule right here. All right, so I'd like you to practice the rest of these. So pause the video, practice them, and then come back and look at what they look like to check your answers. And then there's also a worksheet for you to practice as well. So pause the video and come back. Welcome back. Hopefully you did these and are checking your answers. So NH3, nitrogen with a lone pair bonded to 3 hydrogens with single bonds. Oxygen is 2 oxygens double bonded, and each of them have 2 lone pairs on them. Let's see, carbon monoxide, carbon in the middle, carbon dioxide, carbon in the middle, 2 oxygens on the side, both double bonded, and then each of the oxygen has 2 lone pairs as well. CH2Cl2, hopefully you figured out that carbon should be in the middle because it forms 4 bonds. The hydrogen and the halogens are on the outside, all single bonds, and the chlorines each have 3 lone pairs. PCl3, the phosphorus is in the middle with 2 lone pairs, and then bonded to 3 chlorines, each with 3 lone pairs. And then finally, C2H2, the carbons are in the middle, triple bond between them, and then a single bond between the carbon and each of the hydrogens.